Welcome to the Health Compass podcast. I'm your host, Maya Adam, Director of Health Media Innovation at Stanford Medicine.
This is the beauty of Stanford, right? There's very few medical centers in this country where the engineering campus is on this side of the street and the medical campus is on this side of the street. So when we got connected, I went over to Renee's lab and she's showing me these just incredible pictures of this robot literally dissolving a blood clot. And so then I flip open my laptop and I'm like, well, here's what I do in stroke patients, and kind of show her how we're dragging blood clots out, and we're kind of looking at each other like, yeah, we have to do this.
Strokes that are caused by blocked arteries are among the most time-critical emergencies in medicine. In stroke care, minutes matter, and so does precision. The difference between paralysis and recovery often comes down to how quickly and how completely a blood clot can be removed. At Stanford, an engineer and a physician came together to rethink that problem entirely. Dr. Renee Zhao is a mechanical engineer who studies tiny origami-inspired robots designed to move through the body to investigate and deliver medication. Dr. Jeremy Heit is a neurointerventional radiologist who treats stroke patients every day and sees that better tools are urgently needed. Together, they developed something unexpected, the millispinner, a tiny device that spins a clot, compresses it, and makes it easier to remove. It's a breakthrough born out of curiosity, proximity, and collaboration across disciplines. Today, we're talking with Renee and Jeremy about how this discovery happened, why it matters for stroke care, and what it can teach us about innovation at the intersection of engineering and medicine. Here's what they had to say. Renee and Jeremy, welcome. Thank you so much for joining us today.
Thank you for having us.
Yeah, thanks for having us. This will be fun.
It's unusual for me to have two of you on in one discussion. It's going to be very exciting. I look forward to it. Renee, can I start with you? I often ask our guests to share a story, like a moment in their careers or their personal lives that shaped where they are today. Can you share something like that with us?
Of course, I think I share a lot of experience with my students, and one story I always share with my students and the younger researcher is that when I was doing my PhD, it was close to my finishing point to get a PhD degree. I was always telling myself that's the end of my academic career. I want to go to industry 100%. And I want to do something that is real and is like creating things that you can actually see and touch, and it has something that is relevant, very relevant to our daily life. So that was what I decided to do. I went to industry, spent some time as a developer in a software company, and I learned really a lot, and it was a great experience. But I also decided, okay, that's time to go back to academia. The reason was that so my personality, I really enjoy challenges, and then being able to define the problem you want to solve instead of being told of what you really need to do to get the work done. So I enjoy challenges. I enjoy the exploratory environment where we can create problems, exciting problems to solve.
I love that. Jeremy, what about you? Was there a pivotal moment or decision that you made that sort of shaped where you've ended up?
It's an interesting question. So number one, I'm really glad Renee came back to academics, because that would have been a travesty. Lost that. So thank you. I think, your career when you're younger, especially for people going into medicine, I think people feel that it's very linear, right? Because you go to medical school, then you go to residency, then maybe you do a fellowship, then you get a job. And if you kind of look at that, it just looks like you're graphing a here's your path, and you just get on the escalator and you keep riding it. But I think that's definitely not how life plays out. It's actually, there's a tremendous amount of zigzagging that goes on, and how you march through that path can be very circuitous. Who you bump into can really change your direction substantially. And so just for, young folks listening to this, keep in mind that this is the journey, and you're not on an automated, ride that's going to get you to the top. There's a lot of forks in the road. So when I came out of doing my MD PhD at Stanford, I thought I was going to go be an internal medicine subspecialist. I was going to be a pulmonologist or a cardiologist, and I was going to have a basic science lab that was studying, development of one of those two organs, and then I'd be seeing patients at the same time. And here I am, like, doing things in the brain. So it's not what you think you're going to necessarily do, and a lot of that's who you bump into. And so when I started my clinical rotations, I just clicked with one of the chief residents in neurology, who we just, personality-wise, we got along. We had a lot of fun together. And he was really interested in this field I'd never heard of called neurointerventional radiology. And so when I was a med student on the neurology rotation, we actually saw a patient who had a basilar stroke. It's a big artery in the back part of the brain. That's arguably the most important artery in your body, because if you lose the brain that supplies, you cannot be alive. And I saw one of my, who later became partners, go up and pull that blood clot out and restore the blood flow. And you're sitting there looking, like, okay, this is pretty cool. And, I was very captivated just by the angiographic anatomy of the brain. It was a part of the human body I never thought I'd be interested in. And then here I am, so many years later, this is what I do. So the escalator I thought I was on definitely was not the one. And so just encouraging people to keep an open mind, and keep an open mind to who you run into and where that can take you. And I think that has certainly been the case for Renee and I as well.
I would love to hear more about that. Renee, can you tell me what you were working on when you first met Jeremy?
Of course. So we all started from a work we published now is so 3 years ago we published a paper that was about a magnetically activated soft robot that was 6-7 millimeter big, and we were thinking about it created a very interesting suction mechanism, and we thought if we can downsize the system so that it swims in the blood vessel and can suck the clot. That was the initial thought. So we did some preliminary testing and downsized the system and tested in a tube that's with a similar size of blood vessel, like 3 millimeter size. And there was one time my student was presenting a poster. It was at an internal event, and a common friend connected me and Jeremy. And Jeremy was all very interested in that. So he visited my lab, and we showed the demonstration to him. And that's all everything started. It was like, we didn't know each other by that time. It was really a lot of fun just by the way that we were connected, and how much time that Jeremy later on committed to the project without, knowing because there was a huge risk, right? Both of us, we didn't know where the project would be heading, and we didn't have any funding to start it. We were just working together and started to apply for internal grants to support our project. So that was completely unexpected.
It was super fun.
What was that moment like for you?
No, so it's great. This is the beauty of Stanford, right? There's very few medical centers in this country where the engineering campus is on this side of the street and the medical campus is on this side of the street. And so not many people can walk across the street very easily. And here, when it's 70 degrees out in the middle of December, you can go do that anytime you want. So we got connected, went over to Renee's lab, and she's showing me these just incredible pictures of this robot literally dissolving a blood clot. And so then I flip open my laptop and I'm like, well, here's what I do in stroke patients, and kind of show her how we're dragging blood clots out. And we're kind of looking at each other like, yeah, we have to do this.
That was amazing. I have to say that we didn't have a lot of confidence in the very early prototype that we developed in the lab. We were questioning us a lot because we didn't know what was the clinical pinpoint. We had completely no idea what was the technology used to treat it, is the technology used to treat stroke patients nowadays, and we didn't know what the spinner would be doing to change the field, and we're hoping that it would change the space, right? But we had absolutely no idea. We were just having something that's spinning, it shrinks the size of the clot. That's it, that we had the demonstration. And then Jeremy came, and then we started to really developing the real prototype for stroke treatment.
Huh. And how does that work exactly? Does it have to do with centrifugal force, or what is it that causes the clot to actually shrink?
That's a very good question. A lot of people would think that's a centrifugal force, and we actually did a lot of very careful study to prove that the way that those millispinner works is to densify the fiber network through the compression and shear. I know this is probably a little bit difficult to be understood by a general audience, so I will explain. So, and then our paper, we showed a very close or very similar replicate to what the blood clot is, which is the cotton fiber. If you have a cotton ball, right? So that's everybody will know what a cotton ball is. It has a very loosely distributed fiber network, which is very similar to the fiber network in the clot. So it all depends on the clot. It's kind of driven by, or it's relevant to the micromechanics of a blood clot. And let's talk about the composition of the blood clot, which is pretty much all the fiber network constraining red blood cells. That's what is a composition in a red blood clot. So what the spinner is doing is that when it spins, it generates a flow field to compress the blood clot, and in the meantime, it generates this high friction so that you're rubbing the blood clot like you're rubbing a cotton ball. So you can imagine that if you put a cotton ball between your palms and rub it, and you are applying compression force and a very high friction, and eventually you will get a very densified fibrin network core and with extremely small size. So that's a tiny little core. That's eventually what we're removing from the blood vessel, right? So we can shrink the clot to only 5% of its initial volume, really shrink it in place. And comparing to the existing technology that's out there to treat stroke, I mean, Jeremy can talk more about this, but it's really just based on aspirations like pumping. You turn on the pump, right? So you're hoping that the low pressure, the vacuum pressure will be able to remove or pull the clot into the catheter, or using a stent retriever to pull on the clot. But I mean, a lot of the devices, they're in larger and larger dimension, right? So they're making just devices larger and larger and bigger. So we are approaching the problem from a completely different or opposite direction. So instead of making the device larger, we're making the clot smaller. So shrinking the size of the clot to remove it, which is really very, very different from what's out there.
Interesting. And Jeremy, how does one as a clinician go from like seeing this invention and thinking this could really be interesting in my field? What are the next steps then to actually testing it and getting it to patients?
Yeah, this was what was so compelling, right? As like Renee's saying, the stroke it's like a heart attack, but it's a heart attack of the brain. So if you block an artery going to the brain with a blood clot, you cut off the blood flow. So that's not good. So you have to get the blood clot out and get blood flow back to the brain. And as Renee described, sort of my job is to be a plumber. I'm going up and I got to get that clot out. But the tools, as Renee said, I can try to suck it out. I can try to put a little device up to grab it and yank it out. But neither of those changes the clot. It's just the size and the composition of the clot that's there. I just have to deal with that. I don't have any way to change it. So to see a device when Renee was showing what they could do where, whoa, you're changing the clot. And by changing it and making it smaller, that would make my job easier to get that thing out of there. This is a really good idea. And that's what we kind of ran with. So how do you go from that and, Renee's incredible lab with her students that they can, show that this works in tubes and build fancier models that mimic human anatomy and show that it works in there. What do you have to do next? Well, number one, I don't know how many prototypes did we go through, Renee? I lost track.
Hundreds, definitely hundreds. I can't count, it's a lot.
So you have to, iterate. You got to find what doesn't work. It breaks for a mechanical reason. There's a safety concern that I raise, like, oh, we cannot do that in a patient. We need to fix this. And Renee's got to go and like come up with a super clever way to make it safer that I'm going to be like, oh, that looks good. I just get to be the like problematic guy, like, oh, no, that. And then she goes and fixes it. I'm like, oh, okay. But you have to get all these different variations and say, we think this works. Then you put it back into these flow models in Renee's lab, where we would pick the toughest anatomy cases we could think of that I would encounter in a patient. Does it work in those? Great, it does. But that's all in a like very artificial setting, and it's good, but it's literally on a benchtop. The next thing you want to do is say, well, what about in a biologic system? So then you start to do some animal testing, and usually we use pigs for these sorts of tests, because now you're in a situation where, okay, what about moving blood? What about an actual artery wall instead of a plastic tube? Those are very different structures. Does it still work? And so we were able to show, yes, it still works in an animal setting. So then once you kind of do those things, then you're starting to say, this is looking like it could work in a patient. And then what you got to do is you have to move, generally you get as far as you can in an academic setting, which we did. And then you have to try to move it out to, a company that can commercialize the technology or a variation of the technology and try to get it into patients, which is a whole other long process. It was really fun to be able to do all that we did together in the Stanford system, which again, not a lot of places can do this, because we're very lucky to be in a center with a lot of resources.
Okay, so talk to me about those hundreds of prototypes. Maybe, Jeremy, this is a question for you. Was there a moment where you felt like, this is just not working? Like, how does a scientist keep going through that? And what does that feel like?
We definitely had, I think, a few moments, Renee, where we were like, ooh, okay, this is going to be a problem.
Yeah,
My big thing
I, I
was,
feel like I feel like Jeremy is always a cheerleader on this. I was the person that, oh my God, will this actually work? Jeremy was always there cheering me up.
I love that. Jeremy, how did you keep that positivity?
well, you got to sense something can work. And actually, it was great. Every time we had a failure early on, which was a lot, it's just a new problem you have to address. And Renee's persistence is not to be underestimated. She will figure it out, and her students are so good together. They always figure it out. So my big thing was twofold. And when we first started looking at this, my concerns were, number one, okay, we're shrinking the clot, but we're just going to send a bunch of small clots flying away in the brain, and that's not good. So that was big concern number one. And then number two, I was like, okay, you're showing me this spinning thing, Renee. That looks like a drill. I don't want a drill in an artery in the brain. Like, we can't have a drill. And so Renee said, okay. And then they solved both of those problems. And we had to come up with, first we had to do experiments to show that as you shrink the clot, you're not just sending smaller bits of clot flying. And that's what we found. And I was like, oh, okay, well, that's really good. This is great. I was wrong on what I thought would happen. And that's still the number one question I get asked by physicians, by the way. And then the drilling part, we actually had to do experiments to say, well, is this a problem? Because the first bit, the first device was actually, Renee would print it in her lab, so it was a plastic, and she'd be like, it's fine. And you can push it in her hand, and it was fine. But then we started pushing against blood vessels, and it was not fine. So it did act like a drill. So we had to make sure we had a big safety component, that this thing couldn't actually stick out. It would be confined in a catheter for safety. And the engineering fix was just so clever, so clever. And as you see these setbacks and then successes, and then suddenly you get to a point where you're marching forward. Sometimes it's, 2 steps back, 3 forward, but then as things get refined, you're just stepping forward every time you do something. And that was really exciting to see. And that's when we were really roaring forward very quickly.
And are there other applications of this in other disease states?
It's so the spinner is a platform technology. It treats clot. The clot can be in a lot of different places in human. So we work together for a stroke indication, but it can also work for heart attack and pulmonary embolisms and deep vein thrombosis, and it also works for kidney stone. So those are different things that we've tried.
I'm fascinated by this coming together of disciplines. And I wonder if you can talk to either of you can talk about other experiences you might have had where collaboration between two fields, catapulted you forwards. And is that something that happens very frequently, or tell us a bit more about that?
I can
Um,
start. So it doesn't happen enough.
Mm,
Okay? And then that's just 100% the case.
mm,
Um, it is so critical. And that's where really major steps forward happen. It's sort of it's sort of if you read, for example, like we're all very tempted to just read literature in our own field. You have to be very intentional about looking outside your field because that's where you really put together really unique connections. And that's the same thing as talking to people outside of your discipline. And again, I give Stanford as an institution a ton of credit because, Renee's students and other students in engineering come over to the medical side and see what we do. And then we do our best to go over to that side and see what the engineering folks can do. And that's effort, right? Everyone's busy. You've got to take time out of your day to see that. But when you do that and you cross pollinate, you really get a sense of, wow, I could do that for this in my practice. And that's where it starts. But that's step one. I mean, just making a connection doesn't make any of this happen. Then you've got to have people come together and do the work. And I think that's where Renee and I really excelled is we both can work hard, we can work efficiently, we can write, we can seek funding, we can execute. And I think the two of us together do that really well. But you also have to have the right personalities. Um, there's a lot of big ego in medicine. There's a lot of big ego in engineering. To do this kind of stuff, you need two people that can check their ego and work together. And I think that was just, we had all of these little bits between the two of us come together that really made this work in a spectacularly effective way.
mm. Jeremy, how could one more formally sort of increase the likelihood of these interdisciplinary projects coming about? Do you have any ideas for maybe cross-disciplinary conferences or meetings or ways in which other institutions might be able to facilitate bridges like this?
That's a great question, Maya. And I think Renee, I'm sure will have some thoughts on this too. So things that are done that I do think help are you really purposely promote multidisciplinary collaboration. So you can do that by holding a meeting and
Mm,
saying, we want engineering and medicine to come to this. Let's get everyone in the same room and talk. There are buildings on this campus where the lab space is intermixed between very different disciplines so that when students are walking past each other and saying, hi, hey, what do you do? Here's what I do. And that can try to, generate ideas. And I think there's something to that. I think that those are helpful, but again, it's not, you need more than that. What I don't know how to solve is how do you solve the chemistry part, right? It's kind of like dating. You've got to there's got to be a spark that's going to make sure that you've got all the pieces there. It's got to work together. And that's a little bit trickier thing to solve. So you can kind of do everything to maximize that interaction happens. But the two people that can work really well together, you got to find each other and then make it happen.
mm.
And Renee, tell me, like you probably have a bunch of other thoughts on this, but it's complicated.
it is complicated and it's also difficult. I would say, um, I mean, what the collaboration between my lab and Jeremy, this is really this very unique, and I didn't expect this, and I learned a lot through our collaboration, because you need to be very open-minded to expose yourself to new opportunities. A lot of everybody at Stanford is busy. We all have our own thing to do. And what I really appreciate, that Jeremy came and really actually put a lot of time and effort on this, something that he had nothing to do before, and he joined us, and then we really started to develop this technology together to get to where we are today. So that needs a lot of courage, and well, courage in the sense that you were willing to take the risk. The risk is that eventually you spend a lot of time and effort, it may turn into nothing, right?
Mm,
So not everybody can take that risk. So being very open-minded and also respect other people's understanding of specific problem. That is also what I learned a lot through this collaboration, because from the very beginning, I feel like we speak completely different language. And what we care as engineers, Jeremy doesn't care at all. And I was like, how come you don't care about this? This is so important. And eventually I realized that we need to really be able to talk to doctors and know the clinical pain points and know what we need to address. We need to address real problems instead of artificial problems that are from engineering aspect can be very important, but from clinical aspect, it might not be that important at all, right? So a lot of understanding other people's way or from other aspects to approach the problem and eventually converge, I think that is very, very important. So open-minded and also trust each other. I think those are all very important things to consider when we come up with ideas that require multidisciplinary efforts.
And learning the problems is, because again, it's very easy. Renee has no shortage of creativity and the ability to build anything you want. But you can build a tool, it's got to have an application. So it really takes effort to understand like what really are the problems you are facing. What problem do you run into in patients that is not solved right now? And then can you design something that addresses it? And I don't think it always happens that way, Renee. I think there's a lot of things where a tool's developed and then you go looking for a problem to fit the tool. And that can work sometimes. You can get lucky. But it's far better if you say, here's the specific problem, and then you innovate the tool to address the problem. And that worked really well for us.
Excellent. Okay, I have a nearing the end of our conversation type of question, and that is, if you reflect back on this whole chapter, what will be the one thing that stays with you, the one moment that really you'll never forget?
I can start. I think because when we started developing the Millis spinner technology for clot treatment, we were not expecting the fibrin densification and clot shrinkage functionality. It was just the spinner creating a localized section, and we wanted to use that to suck blood clot. We were not thinking about changing its size or changing its microstructure. It was all unexpected. And I think the one thing I really value through this experience is that always embrace the unexpected results and uncertainties, because these are where the most transformative opportunities are born. I think this is really important because our very common or normal mindset, especially for my students, when you start a project, right, so you have some expectations or some results that you're expecting, some goals that you want to achieve. But if you focus too much on that, things will always go wrong. Nothing will go 100% as expected. If you get a 100% expected result, that means that your problem is not that exciting. You already know what you're expecting. So oftentimes those things are not following what you thought about, or it went wrong. And instead of focusing on, oh, it's not the thing that I expected, thinking about what it actually opened up, something that's very new. I think that's the most exciting part of doing research.
Great points. Jeremy, what about you? Any moment that stands out as one that will remain unforgettable?
I think it's, for me, it's lessons learned and experiences. So first off, I completely agree with Renee. I mean, this is a project and I think a success story that emphasizes the importance of curiosity, because it's very easy for an unexpected result to say, well, it didn't work and walk away. And that's not what she did. It's not what her students did. They were curious at what they were seeing, and that really took us down the path to figuring this out. So you've got to have that curiosity, and then you got to have the tenacity to keep following through. And I think there are innumerable stories in science of this nature, right? And I don't know how many Nobel Prizes start with the same kind of story. So that is a well-learned lesson that I think for any young physicians, any young scientists listening to this, that's really critical. So that was super fun to be a part of, and that's something that I'll always remember. And then there's the whole project. There's so many kind of ups and downs and high points and low points, but kind of the best part of this is having gotten to work with Renee, having gotten to know Renee really well. Like, we became such good friends doing this together. And those sort of interactions and relationships, that's the best part, right? I mean, you come to the end of this and you've got a companion and a friend that you didn't have before, and you did this really fun thing together, and we'll get to keep doing fun things together. That's the best part. So who you meet along the way, it is not to be underestimated. And I hope everyone can keep that in mind for their own careers too.
Well, that seems like a wonderful place to end. I'm so grateful to both of you for your time, and congratulations on this exciting discovery. And I wish you both all the best in the future.
Thank you so much, Maya.
Thank you for having us. This was a lot of fun.
Special thanks to Renee and Jeremy for joining us today and for giving us a look at how innovation happens when clinicians and engineers push each other to dream beyond what either thought was possible. Thank you for listening to Stanford Medicine's Health Compass podcast. If you'd like to hear more conversations like this one, you can follow Health Compass on the Stanford Medicine YouTube channel or any podcast platform you use. Stay well and see you next time.